We ask a lot of big questions. Where did the universe come from? What is consciousness? And right up there with them is a question about time. Is there a smallest possible piece of it? It feels like a strange question at first. Time seems to flow. It feels smooth, like a river. You can have a second or a half second or a tenth of a second. You can use a stopwatch to measure a millisecond, a thousandth of a second. Scientists can measure nanoseconds and picoseconds. It seems like you can always chop time into smaller and smaller bits forever. If you have a slice of time, you can always imagine cutting it in half, and then cutting that half in half. On and on. There seems to be no end to it. This idea of infinite divisibility was the standard view for a long time. It's what Isaac Newton believed. He thought of time as something absolute, a great cosmic clock that ticked at the same rate for everyone and everything in the universe, everywhere. It was the ultimate backdrop. It was independent. It just was. And in this view, the river of time was perfectly smooth. You could zoom in forever and never find a ripple or a gap. It was continuous. For centuries, this made perfect sense. Our daily experience supports it. When you watch a ball fly through the air, it moves smoothly. It doesn't jerk from one spot to the next. It occupies every single point along its path. Time feels the same way. The present moment seems to bleed seamlessly into the next. There are no jumps. But then, about 100 years ago, physics got weird. A German physicist named Max Planck was working on a problem that had stumped everyone. It had to do with heat and light, specifically how objects glow when they get hot. The old theories predicted that a hot object should release an infinite amount of energy, which was obviously wrong. They called it the ultraviolet catastrophe. Planck found a solution, but it was a strange one. He had to assume that energy didn't come in a smooth, continuous flow. He proposed that it came in tiny, discrete packets. He called these packets quanta. This was a revolution. It was like discovering that water wasn't a continuous fluid, but was actually made of individual H2O molecules. Or that a beautiful smooth photograph was actually made of tiny dots of color, or pixels. The world at its most fundamental level wasn't smooth. It was grainy. This idea launched quantum mechanics, a whole new way of understanding reality. And it made people start to wonder, if energy is grainy, what else might be? What about space? And what about time? This is where we get to the heart of the matter. Physicists started to play with the fundamental constants of the universe. These are numbers that seem to be baked into the fabric of reality. The speed of light, which is the ultimate speed limit. The gravitational constant, which sets the strength of gravity, and Planck's own constant, which sets the scale of the quantum world. A physicist could take these constants and combine them in different ways to get fundamental units of measurement. They could get a fundamental length, a fundamental mass, and a fundamental time. The smallest possible unit of time that comes out of these calculations is called the Planck time. Now, we have to be very clear about how small the Planck time is. It is an absurdly mind-shatteringly small interval. It is roughly 10 to the power of minus 43 seconds. That's a decimal point followed by 42 zeros and then a 1. There's nothing in our everyday experience that can prepare us for a number that small. Let's try to put it in perspective. Like, the time it takes for you to blink your eye is about a tenth of a second. A millisecond is a thousandth of a second. The fastest chemical reactions are measured in femtoseconds, which are a millionth of a billionth of a second. The Planck time is to 1 second what 1 second is to the age of the universe many times over. If you were to slow down time so that 1 unit of Planck time felt like 1 second, the old regular second would last for billions of years, longer than the entire history of our planet. So the Planck time is very, very small. But is it the smallest possible unit of time? Is it a pixel of time? The answer is maybe. It's our best guess, and the reasoning behind it is profound. It's not just about our inability to measure anything smaller, it's that our very understanding of the universe suggests that the concept of time itself breaks down at this scale. Here's why. We have 2 great theories that describe the universe. General relativity, Einstein's theory, describes the big stuff: planets, stars, galaxies, and gravity. It treats space-time as a smooth, bendy fabric. Quantum mechanics describes the small stuff: atoms, electrons, and the other forces of nature. It treats the world as grainy and probabilistic. For the most part, these 2 theories work in their own domains. But at the Planck scale, they collide. To look at something as small as the Planck time, you would need an incredible amount of energy. According to quantum mechanics, the more energy you pack into a small space, the more unpredictable things get. Virtual particles pop in and out of existence, creating a frothing, chaotic foam. According to general relativity, energy and mass warp spacetime. So, if you concentrate enough energy to probe the Planck time, you would essentially create a tiny, fleeting black hole. Think about what that means. To measure a duration of time, you need a start point and an end point. But in this scenario, the start point and the end point are scrambled. The immense energy required to see this scale would warp space and time so violently that you couldn't tell which way was forward, backward, up, or down. The very fabric of space-time would become a quantum foam, a chaotic mess of tiny temporary black holes. Causality, the idea that a cause comes before an effect, would lose its meaning. You couldn't say an event happened before or after another event, because the timeline itself would be shredded. So, the Planck time isn't just a limit on our technology. It seems to be a fundamental limit on reality itself. It suggests a point where the question, what happened in a shorter amount of time, stops being a meaningful question. It's like asking what's north of the North Pole. The concept of north breaks down at that point. Similarly, the concept of time as a smooth, forward-flowing sequence of events seems to break down below the Planck time. This idea is incredibly compelling. It suggests that the universe has a fundamental frame rate. Like a movie that seems to show smooth motion but is actually made of 24 still pictures per second, maybe the universe progresses in a series of tiny, discrete steps, each one Planck time long. We don't notice it for the same reason we don't see the individual frames of a movie. The refresh rate of reality is just too fast for our senses or our instruments to detect. But we have to be honest, this is all theoretical. We have never directly observed anything happening at the Planck scale. We can't. The energy required to build a machine that could probe this scale is so far beyond our current capabilities that it's not even worth discussing. It would be like trying to build a skyscraper using only beach sand and a plastic shovel. So the Planck time is a number that comes out of our theories, not a number that comes from an experiment. This leads to a debate among physicists. Is the Planck time a true physical pixel of time? Or is it just a signpost that tells us where our current theories fail? Some physicists believe that space-time is truly quantized. They are working on theories that try to describe this grainy reality. One of the most prominent of these is called loop quantum gravity. Loop quantum gravity takes the idea of quantization seriously. It proposes that space itself is not an empty void. It is a network woven from tiny, indivisible loops of gravitational fields. These loops are on the scale of the Planck length, a sister concept to the Planck time. You can't have a smaller piece of space than one of these loops. It's the atom of space. In this view, time is not a fundamental thing that flows. Time emerges from the changes in this network. Imagine the network of loops reconfiguring itself. Each change is a tick of the cosmic clock. Time, in this theory, is the measure of these changes. So, there's a small step. A process can't happen in less than one change. This directly leads to the idea of a smallest unit of time, naturally. Then there's another major contender for a theory of everything called string theory. String theory has a different take. It suggests that the fundamental constituents of the universe aren't point-like particles, but tiny, vibrating strings of energy. Different vibrations of these strings give us the different particles we see, like electrons and photons. In string theory, there is also a minimum length scale, the size of a string, which is around the Planck length. But its view on time is more complicated. Time is one of the dimensions that the strings vibrate in. Some versions of the theory suggest that our familiar notion of time might be an emergent property of some deeper, more complex reality that doesn't have time as we know it at all. So, while it hints at a fundamental scale, it doesn't necessarily give a simple pixel of time in the same way loop quantum gravity does. So we have these different theoretical camps, all trying to understand the nature of space-time at its most fundamental level. They don't all agree, but they all point to the Planck scale as being incredibly important. Since it's the battleground where our best ideas are being tested, at least on paper, there's also a more philosophical and perhaps more mind-bending idea called digital physics. This idea suggests that the universe is, in some sense, a giant computation. The laws of physics are the algorithm. If reality is a computation, then it must be processing information, and any computer, even a cosmic one, has a clock speed. It can only perform a certain number of operations per second. The smallest unit of time, in this view, would be the clock cycle of the universe. It would be the time it takes for the universe to perform one fundamental logical operation. This is a speculative idea, but it connects this deep question of physics to the world of information and computation. Thinking about a smallest unit of time can also help with some very old paradoxes. The ancient Greek philosopher Zeno came up with a series of paradoxes about motion. In the most famous one, the fleet-footed Achilles is in a race with a slow tortoise. The tortoise gets a head start. For Achilles to catch the tortoise, he must first reach the point where the tortoise started. But by the time he gets there, the tortoise has moved a little bit forward. Now Achilles must reach that new point. But by the time he does, the tortoise has moved forward again, just a tiny bit. This goes on forever. Achilles has to cross an infinite number of ever smaller gaps. Zeno argued that, logically, Achilles could never catch the tortoise. Of course, we know in the real world that Achilles will quickly overtake the tortoise. But the paradox challenges our ideas about space and time. Zeno's argument only works if you can divide space and time infinitely. But what if you can't? If there is a smallest unit of space, a Planck length, and a smallest unit of time, a Planck time, then the problem disappears. There is no infinite series of smaller and smaller gaps. Achilles doesn't have to cross an infinite number of points. He just has to cross a very, very large but finite number of space pixels in a finite number of time ticks. Once he has taken the last step, he has caught the tortoise. The grainy nature of reality solves the paradox. So, where does that leave us? The question, is there a smallest possible unit of time? Doesn't have a simple yes or no answer that we can prove. But the evidence from physics strongly points towards yes. Our most successful theories, when pushed to their limits, tell us that the idea of a smooth, continuous river of time is probably an illusion. It's a very convincing illusion, one that works perfectly for all practical purposes in our daily lives. But at the bottom, reality seems to be different. It seems to be built on a foundation of discrete, indivisible units. The Planck time is our best candidate for what this fundamental unit is. It's a theoretical boundary where our old physics dies and new physics must be born. It represents the scale at which space-time is no longer a passive stage for the drama of the universe, but becomes a chaotic, churning actor itself. The implications are hard to grasp. It means that change in the universe might not be continuous. It might happen in a series of incredibly rapid, staccato steps. The universe might be rebooting itself every 10 to the minus 43 seconds, updating the position and state of every particle. It's a staggering thought. It means that the smooth flow of existence we experience is a product of our scale. We are too large and our senses are too slow to perceive the fundamental graininess of the world. We see the photograph, not the pixels. We hear the music, not the digital samples. This idea also changes our perception of emptiness. The space between atoms is not just nothing. And the time between events is not just a void, it's the arena for the most fundamental processes of the universe. The quantum foam, the popping of virtual particles, the weaving of the fabric of space itself. The search for the smallest unit of time is more than just a quest for a number. It's a quest to understand the very nature of reality. Is the universe analog or digital? Is it continuous or discrete? The answer seems to be that it's digital, at least at the level we can currently conceive. And that the smallest tick of the cosmic clock, the Planck time, defines the ultimate resolution of our universe. We may never be able to build a clock that can measure a single unit of Planck time. We may never see the pixels of reality directly, but the fact that our equations point to their existence is one of the most profound discoveries in science. It tells us that there are limits. There is a smallest piece of space you can have. There is a smallest tick of time that can pass, and in a universe that so often seems infinite and overwhelming, there's something strangely comforting about that. It suggests that even time itself has a fundamental building block, an indivisible ultimate moment. The atom of time, and the universe is built, one of these moments at a time. The question remains open, a deep and driving mystery at the frontier of human knowledge. We keep asking it, and in the asking, we learn more about who we are and the strange, grainy, wonderful universe we inhabit.